Hello class, in this video we will be continuing our lecture on polar and parametric coordinates, as well as working towards how do we do calculus in polar and parametric form. Sorry about class Wednesday. Usually I get up about 5 a.m. and my body apparently did not agree to my alarm. I don't even remember it going off at all. And I woke up at 8, and yeah, it's kind of embarrassing, so I do apologize for that. But in this lecture series, we'll continue where we left off on Monday, as well as going a little bit further, and we'll get as far as we can before break. And yeah, hope you all do have a good spring break. And yeah, so anyways, let's get onwards where we left off. So we spent some time talking about parametric equations, how to do tangents and area in those forms. And we were working on polar coordinates in the last couple classes. The last little bit before we get into calculus of the polar curves, I want to talk a little bit about polar equations and conversion between them. Because in parametric form, I don't know, parametric equations are a little bit simpler in some sense because we just have this parameter t that defines both x and y as separate components to those equations, where in polar form, r and theta just have a different sense of meaning. So when we're looking at polar equations such as that of the cardioid or the rows, which I'll leave for you guys to graph on your own, they work very differently. They're very circular in nature, and they take a little bit of a different strategy to graph them properly. But that being said, I wanted to talk about how to convert from polar and parametric equations back and forth, just in case you wanted to try to sort of understand what something looks like. So say, for example, we're looking at the equation r is equal to 4 cosine theta, r is equal to 5 secant theta, and so forth. There are ways to sometimes convert polar equations into rectangular form, or into, a normal, quote-unquote normal, implicit or explicit equation involving x and y. And so the key always to conversion is by using the basic conversion relationships. And as we talked about in class, these are just, basic trigonometry where if r and theta represent the distance to the origin and the angle theta with respect to the polar axis, then our basic trig SOHCAHTOA will apply. So x equal r cosine theta, y equal r sine theta, and tan theta equal y over x. Those are just SOHCAHTOA. And of course, the Pythagorean Theorem. These are things you should remember always if you're thinking about the relationship between parametric coordinates. And in Calc 3, I think I mentioned this, but just in case I didn't, these relationships are sometimes used in what we call spherical or cylindrical style integrals. And so these, relationships will come back later, and it's just good to remember those things. But so say we're looking at a polar equation such as these, and the equation 2 plus 2 cosine theta is the equation of a cardioid. We saw what that looked like when we graphed this in class. But what if we wanted to know what do these look like in rectangular form? Well, one strategy that I recommend is, well, if we want to convert r into x and y, we can always think about it as Pythagorean theorem. So r squared is always equal to x squared, y squared. So I kind of imagine you could think to square both sides here, but the problem with squaring both sides of the equation, well, number one, is that can cause some problems from the mathematical side, because squaring both sides of an equation is problematic when it comes to negative values. But also cosine squared, we don't really have a method of converting cosine squared into x and y in a simplistic relationship. So what's actually an easier strategy, which we can use in this particular case, is if we multiply both sides by r instead of squaring both sides. So if I multiply both sides by r, what I would have is r squared is equal to 4r times the cosine of theta. And now it becomes more clear about how this equation can be represented in rectangular coordinates, because, well, r squared is directly x squared plus y squared, and r cosine theta is equal to x. So if we go ahead and put this stuff in, x squared plus y squared is equal to r squared is equal to 4 times r, and again, r cosine theta is just x. So what we have is 4x. And this would be the equation of a circle with, directly the equation x squared plus y squared is equal to 1 is the general equation of a circle, but this 4x, we could move it to the other side and combine it But we could also use a calculator to graph it in polar form. So, in the in a TI-84 or similar calculator, we just need to change the mode of our calculator to polar form. And then we can type our equation into the y equals menu, which will change to r as a function of theta and can be graphed, which we can see this is a circle which appears to be centered at 2, 0 with a radius of 2. But anyways, the point of the matter is that an equation in polar form, which is that of the equation of a circle, may look very different than that of rectangular form. And of course, being able to change coordinates can be helpful in some regards to, rewrite it. And it's a much simpler equation in polar form because there's a lot less, there's less algebraic entities. It's just r equal 4 cosine theta. It has a much simpler feel to it, if you see what I'm saying. And similarly, if you had a function of sine r sine theta, that would also represent a circle centered at a different position in polar form. Now, what about the equation r is equal to 5 secant theta? Well, we could rewrite secant as using trigonometric identities, because we know that secant is the reciprocal of the cosine function, or 1 over cosine. And I could just multiply cosine by both sides. The reason why I would do that is because, well, cosine of r cosine theta, as we know from our fundamental conversion relationships between polar and rectangular coordinates, r cosine theta is equal to x. So what this would leave us with is the equation x is equal to 5, the rectangular version, again, of the same equation. Which, of course, in this case, the rectangular equation is much simpler, or what we're left with is the equation x is equal to 5. And again, we could graph this with a calculator. Let's just see what happens and see if it's confirmed by what our math is telling us. But notice that as this polar equation is graphed, we're left with a vertical line through 5, which is, of course, equal to the equation x is equal to 5. But kind of interesting because vertical lines, horizontal lines, and just general linear functions, you can actually use polar form to graph those. Well, normally they need to be passing through the origin for reasons I don't want to get into. But it's kind of interesting that certain functions, my sort of the main message that I'm trying to communicate is there's a lot of different categories of functions in polar form, and sometimes it's a lot more complex to write a simple object, and some types of objects can't be written in polar form, just like how certain types of objects can't be written with a function or with a parametric equation. And some curves lend themselves to being written in some coordinates. Now, another example is the cardioid. So let's just go ahead and graph this. But we saw one of these in class last time. But let's go ahead and graph 2 plus 2 cosine theta. Gives us the graph of a bit of a heart. And we can't really quite see it because of the pixelization. If we were to zoom in, I'd say about one stage, it should be a little bit more clear. But it has a bit of a heart shape to it, which is why we call these types of curves cardioids. But so how would it be written in rectangular form? That's the question. Well, in this one, we could take a similar approach to we did with the equation of a circle and multiply through by r. And so if we do multiply through by r, what we'd have is r squared is equal to 2r plus 2r cosine theta. And why this is cool is because, well, r squared and r cosine theta, we know that those will translate directly back into rectangular coordinates, because x squared is equal to r squared is equal to x squared plus y squared, and r cosine theta is just equal to x. The issue is what is just r? And you could say, well, I could just write r as the square root of x squared plus y squared. But remember, that is not exactly right, because r could be either plus or minus the square root of x squared plus y squared. So it's not exactly proper to write it that way, though we could, and that would be fine. So another way to kind of get around that is if we solve for r, we could square both sides, and then convert that in terms of x squared plus y squared, alternatively, again, which may have its own problems. But let's go ahead and just do it that way. So if I were to, let's go ahead and subtract 2x to the other side, and then square both sides. Again, I could divide by 2, but I'll just go ahead and leave it there. And now if I square both sides of the equation, remember, you can't square term by term. That is not proper algebraically speaking. what this would leave me with is, well, I'm just gonna leave the left-hand side of this equation as squared and not actually do the algebra, but on the right-hand side I have 4r squared. And of course, r squared makes x squared plus y squared. So 4 times x squared plus y squared. And now we have this equation written in rectangular form. But what I want to, another thing to notice about all of these is none of these are functions. They're all implicitly defined. None of them are explicit because they all fail the vertical line test in terms of what these are. And polar equations tend to not be functions because they're circular in nature, involves theta, and as theta changes, especially when we're involving trigonometric functions, which is pretty typically common in a polar equation, they tend to work in that way. And so summarizing, the equation of a cardioid is quite a complex equation, but there we have it. It's much simpler to take a rectangular equation and change it into polar form, because if we want to, we can always just use the direct x equal r cosine theta and y equal r sine theta. So say I wanted to take this equation and convert it into polar form. Well, basically I could just substitute an r cosine theta for x and r sine theta for y, and that's literally it. But as you probably noticed up until this point, it's pretty standard to write polar equations as solved for r, because typically they are solved as a function of theta. They don't have to be, but usually they're defined functionally based on theta. So if basically what we want to do is solve for r, generally speaking. So we'd have r squared cosine squared theta is equal to negative 7r sine theta. And what I could do is divide both sides by r. Now I'm removing the possibility of r being 0, which is technically, a possibility by doing this. And, what I have is r cosine squared theta is equal to negative 7 sine theta. And then I could divide by, divided by r, I forgot to cancel out the r there. And then I could divide through by cosine squared of theta. And I would get r is equal to negative 7 sine theta divided by cosine squared. And I could simplify this because sine over cosine is tangent and 1 over cosine is secant. So, I could leave it like this, or even use trigonometric simplification and just rewrite it, like that instead. But anyways, what we would wind up with is this equation. And so again, well, what's the point? Well, if we're wondering, well, the original equation is that of a parabola. And if you remember properties of parabolas, that if one of the two, variables between x and y are squared, that's always going to give you a parabola. And if x is squared, it would give us a vertical facing parabola up or down. And if y is squared, it will be a sideways parabola. But basically, this should be the equation of a parabola. Let's just make sure. So again, we can graph polar equations with our calculator. So, sorry, I can't click the negative button with where my thing is. Okay, there we go. Negative 7 tangent of theta divided by cosine of theta. And we can see what we're dealing with. But notice, what we get is the equation of parabola. Of course, this is a way you can kind of check to see if you're converting between one and another. Obviously, it should have the same shape. It should be the same curve you'd expect in rectangular coordinates. And in algebra and most math, we're very used to dealing with rectangular coordinates, not so much with polar. So it's a convenient thing to kind of go back and forth about. Now, another equation we might be wondering is, well, what about y equal 5? How could I convert that? Well, of course, what's much simpler is we can always just use the direct principle. So we could start with, well, y is always equal to r sine theta. So we'd have r sine theta is equal to 5. And again, solving for r is what we're looking for. So I would have 5 divided by sine. And again, we could write 5 divided by sine instead as the cosecant function. So 5 times the cosecant of theta. And what this would give us is the equation of a horizontal line, y is equal to 5, which of course we could check as well. And then the one other thing where I'd suggest a slight difference is, well, let's say you had the ratio of y to x in your equation, or an x squared plus y squared. Those can directly be converted into r. So like in this particular case, anytime we're dealing with x squared plus y squared, that's always equal to r squared. You could plug in r cosine theta and r sine theta, as I did in the previous two examples, But what you'd end up with is r cosine squared theta plus sine squared theta. And as we know, cosine squared theta plus sine squared theta must be equal to 1. So you're going to end up with r squared anyways. That's just an obvious simplification. And if we were to solve for r as we need to, what we get is that r is equal to plus or minus 10 as the polar form of this equation, where you could use positive or negative. It's going to be the same equation regardless, because it's that of a circle of radius rad 10. And as we're looking at the equation, the general rectangular form is x squared plus y squared equal r squared for that of a circle. In polar form, it's so much simpler. If we just do r equal to the square root of 10, that would give us that of a circle centered at the origin of radius 10. Let me go back to zoom standard. Sorry, not radius 10, radius of the square root of 10, which, anyways, it's the same equation, much simpler in polar form. And in polar form, equations of circles and any sort of object which is circular, not exactly circular, but periodic and rotational, such as that of a cardioid or a rose, or things that spin, very, very convenient in polar form, and they often have much simpler representations. In calculus of those curves in polar form tends to be much simpler in polar form, which is why we care about this and why we're getting into this at all. So in the next video, we'll talk about tangent lines, and then we'll move into area. Area is a little bit different in polar form, so we'll take a little bit of time with some of those examples, and then we'll work our way back into arc length in both parametric and polar form.